Well, good morning. Welcome to the midpoint session, the third parallel session for TeVPA 17. Our first speaker is Victoria Kaspi, who will be telling us about fast radio bursts and CHIME.
Hello, can you everybody hear me well? Good, thank you. So it's my first TeVPA meeting and my first time in Columbus, and I'm really honored to be here. And very happy to be telling you about fast radio bursts, something that might be a little off the beaten track of TeVPA meeting, but this is the domain of radio astronomy, and it's a new astrophysical mystery, something I'm going to tell you about, something we really don't understand, these fast radio bursts. You know, you see the cover of Nature from January of this year, mystery objects. I think that's a pretty good description for the time being. Okay, so what are fast radio bursts? So this is a phenomenon that was first discovered or at least published in 2007 in a paper by Lorimer et al. And it consisted, the first event that was observed consisted of a short, and by short I mean a few millisecond burst of radio waves. Today, in the decade that's passed, there's about 24 of these events have been observed. And the sort of signal that you can see, and the first one was detected with the Parkes radio telescope. You can see the dish down there. What you can see is that, just look for the moment at the inset, just a very short burst. This lasts just a few milliseconds on top of noise. And the way that radio waves propagate through ionized plasma, that is through the interstellar medium, or, as we believe for FRBs, through the intergalactic medium, is they're dispersed. So although we believe that the radio waves emitted by the source, whatever it is, it's broadband, so many radio frequencies all emitted at once. The ionized component of the interstellar intergalactic medium disperses those radio waves so that this burst actually arrived swept through the bandwidth. So this is time on the x-axis and radio frequency on the y-axis, here going from 1.2 gigahertz to 1.5 gigahertz, and you can see that the highest radio frequencies arrive earliest. This is classic cold plasma dispersion. It's a 1 over f squared laws, I'm going to show you in a second. And so this, as I'm going to explain a little bit more details, what's telling us that it's probably from far outside the galaxy, and in fact at cosmological distances. It's that sweep, the delay between the top and the bottom of the band. But in any case, just coming back to the overall phenomenon, as I said, there's about 24 of these events have been discovered and reported since 2007. However, because radio telescopes, they have pretty small fields of view, and these telescopes found these as part of radio pulsar surveys, searching for rotating radio-emitting neutron stars. Because the fields of view are so small, even though we've only detected a couple dozen, we can estimate the full sky rate, and it comes out to be very high. We believe that FRBs are arriving at Earth something like 1,000 times per sky, across the whole sky per day. So this is these are ubiquitous. They're just very hard to detect, and the origin right now is totally unknown. We don't understand the mechanism for producing these events. So I just want to explain a little bit more detail. As I said, radio waves are dispersed by cold plasma, and that's that 1 over f squared. This line here is just a channel that we removed due to radio frequency interference. This is the real signal. In software, we de-disperse. That is, we software delay these these frequency channels, and then add them up so that once you correct for this, you get this nice pulse. That's how this works. And the degree of delay here, so there's a constant of proportionality between the time delay from the top of the band and the bottom of the band, goes as this quantity called the dispersion measure. And you can see it's a 1 over f squared law, where f1 would be the top and f2 the bottom. And the dispersion measure is proportional to the integrated electron density. So I say cold plasma, it's really the electrons that are causing this dispersion. And it's the integrated electron density along the line of sight that's causing this. whatever the cause of those electrons, be they in the galaxy or in the intergalactic medium, in a host galaxy, wherever it is. That's why we see that sweep. And just to be clear about why we think FRBs are extragalactic and even cosmological, this is our best model, or one of the best current models for the electron density arrangement, for the electron density column along different lines of sight in our galaxy. So if you're looking down at the Milky Way, and here, this plot is looking down, here's the galactic center, the Earth is over here, so imagine this were the Milky Way, you're looking right down at it. These lines are spiral arms, and the contours that you see here are contours of constant free electron density in dispersion measure units, which are, because it's NEDL, the integral of NEDL, it's parsecs per centimeter cubed, sort of a crazy unit that we use. But that's what these numbers are. So in any direction, and we often use this, well, not often, ubiquitously use this when studying radio pulsars, because for radio pulsars, you also measure a dispersion measure. And with a map like this, if you know the direction and you know the dispersion measure, you can infer a rough distance for a radio pulsar. And we do this all the time. We've done this for years. But the point is for FRBs that within the galaxy, there's only so many electrons. So along any one line of sight, the model has a maximum number of electrons due to our galaxy. That's the maximum electron column density for the Milky Way. And it's well defined in this model for every direction. And so the point is, for this burst that was from the Lorimer et al. 2007 paper, call it the Lorimer burst, along the line of sight to this event, which was in the southern sky, by the way, not too far from the Magellanic Cloud, from the small Magellanic Cloud, the maximum model dispersion measure is 25 in those crazy units. But the observed dispersion measure here is 375. So the discrepancy between the maximum possible for our galaxy, and there is another reliable model. These models are calibrated by the hundreds well, I would say hundreds of radio pulsars that we know of with independent distance estimates. So the model is pretty well calibrated. It's not off by that much. I mean, there's a huge order of magnitude discrepancy here, and this is what's telling us that these events seem to have to come from a very long distance away. So are they at cosmological distances? So this is like the infancy of this field. We're just asking these basic questions. Are they at cosmological distances? Well, there's intergalactic medium models that predict, and there's a few of them, and the numbers are all within something like 20, 30%, that the dispersion measure should go as roughly 1,200 times the redshift. Now, of course, this isn't measured yet, or actually I'm going to show you shortly that we've sort of measured it for one. We have a rough observational handle on it. But that's a prediction that the intergalactic medium has plasma in it also, and 1,200 times redshift. So if you plug in for the Lorimer burst, that 375, subtracting off the galactic column, the galactic contribution, that would imply a redshift of 0.3 for the Lorimer burst. Okay, 0.3, and that would correspond to something like a gigaparsec, which is pretty far. But we know, and you're probably already thinking, that's got to be an upper limit. Apart from the fact there's uncertainty in this number, it's probably the event is coming from some host galaxy, which, like the Milky Way, has its own interstellar medium and electron density content. So the event has to travel through that local, that host galaxy ISM. And so really the total DM that we measure is a sum of the Milky Way component, the intergalactic medium component, where that's something like this expression here, and then the host galaxy, which is unknown. So we don't know what the host galaxy is. The problem, it's discovered with the Parkes radio telescope, a wonderful telescope, but the angular resolution is something like 30 arc minutes. You can't know, if it's somewhere over there, what galaxy it is. So we don't know big galaxy, little galaxy, no galaxy, and we certainly don't know its electron density contribution. So let's say that that you take the total DM, subtract off the Milky Way component, which we think we understand, and then divide it equally between the host and the IGM. If you do that for the Lorimer burst, okay, it puts you roughly 500 megaparsecs, and that's still pretty far. And that puts the radio energy in the event at 10 to the 40 ergs. So 10 to the 40 is the scale here. And I put that down because I gave this as a physics colloquium, and I thought I had to do that. So there you go, 10 to the 40. And then you might say, oh, you know, 23 of them, how are they distributed on the sky? They're roughly isotropic. Roughly speaking, they're isotropic. There's some biases because people tend to search for pulsars in the galactic plane, or you tend to look a little further out. So there are some biases, but I think it's fair to say that they're roughly distributed isotropically on the sky. And so all of these, basically the dispersion measure argument, the cosmological distribution, the isotropic distribution all point toward a cosmological origin, and it suggests that these events could be very interesting cosmological probes, particularly because the Lorimer bursts and even this other one that was just recently reported are really, really bright. For those of you who know radio astronomy units, this Ravi et al. Event that was reported in 2016 is 120 Janskys. So you might not know what a Jansky is, but it's really bright. You can almost detect that with your cell phone if you know when to look. Maybe that's an exaggeration, but certainly it's close. Now, so here's the online catalog of FRBs. This is, you could see this is, probably you can't read this. This is just to show you there's a lot of them. They're mostly detected at the Parkes telescope. And you might say, well, what are these things? They're cosmological. You know some stuff about them. There's more models than there are events right now. And I'm just going to give you sort of my version of what I think is, what are the salient points. The energy, 10 to the 40 erg, sounds high. It's not that constraining. Okay, remember, gamma ray bursts are much more energetic. And by the way, we haven't seen any GRB, FRB coincidences. That doesn't seem to be happening. There's one that's sort of been reported, but it's not clear that it's real. But for the most part, you don't see it. There's easily enough energy in cataclysmic events like supernovae or neutron star or compact object coalescences, but there are problems with those models. For example, you need a low free opacity in order to get the radio waves out. That's difficult. Many papers in literature about this. The rate is too low for compact object mergers. Also, given the intensity and the inferred distances, we know that it has to be a coherent radio emission. That is, the brightness temperatures are extremely high. So we're talking 10 to the 34, 10 to the 35 Kelvin in some cases. We have seen this long ago in radio pulsars. So it sort of smells a little bit like a radio pulsar. On the other hand, maybe there's some beaming involved. And you need something to get the coherence in the radio emission. So it also smells a little bit like a strong magnetic field. In addition, they're only a few milliseconds milliseconds long, so that suggests a compact object from light travel time arguments. So the whole thing kind of smells a little bit like a neutron star, I would think. But you know, before this, I was a neutron star astronomer, so you might think I'm biased. But I'll just tell you quickly about some new constraints that we have on these sources. I just wanted to see. So it smells a little bit like a neutron star, but there's arguments against it. But in any case, we have new constraints on these. For one thing, we've been searching for FRBs using the Arecibo telescope in Puerto Rico. This is Arecibo 305-meter reflector in Puerto Rico. We've been surveying the galactic plane for radio pulsars for many years now using the 7-beam alpha receiver. This is operating at 1.4 gigahertz with a 300 megahertz bandwidth. It's a big high-performance computing job. We collect roughly a petabyte of data as part of the survey. And you can see that of all the FRBs that are known, and this is still true today, one of them was discovered at Arecibo, and that's the one I want to focus on, FRB 121102. That's the date they arrived as their name. So the one Arecibo event, here it is. This was the first non-Parkes telescope event. So we were actually really excited because we were all sort of worried it was something in their software or it was some microwave oven at their location. That's a whole other story. We know that's not the case now. This was found in Arecibo, the first non-Parkes FRB. This one had a dispersion measure of 558, 3 times the maximum DM. You could see it here sweeping through the band, although you see it's much brighter at the top of the band than at the bottom of the band. And that is an unusual radio spectrum. That right away was like, oh, look at that. radio spectra don't tend to be brighter at the high end. The spectral index here is something like +9, which we assumed was due to being this event arriving offset from the radio beam. So radio telescopes, you know, their antennas, their angular power pattern is very frequency dependent. There is phase space for this to arrive off axis enough that you could take a flat spectrum source and make it look like +9. That's what we assumed was happening. But the great excitement came when we saw this event repeat. So no FRB today has been seen to repeat. Until that time, it had been seen to repeat. We looked at it several times and didn't see any repetitions, but kept at it. There was actually my graduate student, Paul Schultz at McGill, who made this wonderful discovery. He was just blown away. One day, we saw it repeat 10 times. And here are the repetitions. Now, these are de-dispersed plots. So again, it's frequency versus time. And in each of these cases where the sweep has now been corrected so that it looks vertical. And you can see they come in all sorts of brightnesses. You could see hugely varying spectra. This was a real shock to us. This event here and this event here were only a few seconds apart, and yet this one has a whopping positive spectral index, and this one has a whopping negative spectral index, like +10 to -10 in a few seconds. The spectra are clearly intrinsic to the source. And since then, as I'm going to explain, we've localized this thing interferometrically. We know exactly where it is. There's no question we're getting it right in the center of the beam when we keep observing it. And the spectra are all over the map. And you can ask me, what is that? And I could say, I don't know what it means. The repeats are highly clustered. This is a plot based on data from a whole big group of people. This is modified Julian day going upward here. This is about 2012. This is about April of 2017. The lines, the different colors are different radio frequencies. These are different telescopes sometimes, mainly Arecibo, but we have some Effelsberg in here. We have some Green Bank in here. And the length of the line is proportional to the length of the observing run, and the stars are when we see bursts. So you see there's long observation stretches where we see nothing. It's just quiet, doesn't cooperate. And then suddenly, boom, a big burst storm, and this is an inset of this burst storm here. So highly clustered events. Now you could ask, why is there only one repeater known? I told you there's roughly 24 of these events, and I say roughly because people sometimes report them on Facebook. But so far, we only know of one repeater. And some of the other FRBs, particularly the bright ones, have been observed for, I don't know, something like 100, 200 hours. In one case, I've heard that they've observed it for 500 hours without a repeat. So why only one repeater? Are there different classes of FRBs? So, you know, you hate to do that with 24 sources and one example, but perhaps, I mean, clearly if it's repeating, it's not cataclysmic. So maybe there's a class of cataclysmic fast radio bursters and non-cataclysmic. But it bothers me, the coincidence that the only FRB detected with the Arecibo radio telescope is also the only repeater. That seems like quite a coincidence. Maybe that's not such a coincidence because many of the repeat bursts are quite faint and could not be detected with any other radio telescope. I say many, not all. There are bursts that are bright enough that you could have detected them with other radio telescopes, and obviously we have with Green Bank, with Effelsberg. So now the question is, what could the repeater be? And as I say, we really don't know, so I'm speculating, and I already gave you some arguments why it's probably something neutron star, or at least there's good arguments for it to be something neutron star-like. I'm not claiming that's the answer. The ideas that are floated around are rotation-powered pulsar giant pulses. You've all heard of the Crab pulsar, and you know it emits giant radio pulses. They're orders of magnitude fainter than the inferred energy scale of FRBs. But still, phenomenologically, they're similar. Magnetar giant flares is also being discussed. There's no observational evidence for giant radio pulses for magnetars. There are some magnetars that are radio sources, and they do emit erratic radio emission, but again, many orders of magnitude fainter than the FRBs, assuming they're all at similar distance scales. I'm going to skip that. I'll just say, just going back to this slide here, the problem with the crab-like giant radio pulsar, giant pulses model for FRBs is just energetics. As I'm going to explain shortly, we've localized the repeater. We now know it's at a cosmological distance, and the energy scale that it implies is way higher than certainly the crab pulsar, and you'd really, really need to crank up the parameters. So for a rotating neutron star, this is the standard E dot spin-down luminosity expression here, goes as P dot over P cubed. For the crab pulsar, the most energetic one we know of, 33 milliseconds. Here's the P dot, the rate of change of the period. That's the E, that should be a dot up there. E dot is 10 to the 38 ergs per second. The repeating FRB we now know is something like 10 to the 42. So you'd have to really crank up the parameters, and there's a lot of there's arguments. It's really hard to make a neutron star with a high enough energy budget, a rotation-powered energy budget to accomplish this. You can see a paper by Maxim Ludikov on this. On the other hand, magnetars look kind of good. Giant flares have few millisecond peaks in the X-ray, soft gamma ray band. We've seen 3 giant flares since 1979 in our galaxy and the Magellanic Cloud. FRBs, the galactic rate is way smaller than we would infer for our own local galaxy plus Magellanic Cloud. So we must be, if this is the case, we'd have to be really sensitivity limited for FRBs. So there's certainly sufficient energy in magnetars. And you say, well, even for a repeating FRB at a cosmological distance, it's getting close. It's getting a little uncomfortable. It depends on its activity lifetime. It couldn't be longer than something like 100 years. So just coming back to the repeater, I keep sort of hinting, you may have heard about this. Because you have a repeating object, and now you can localize it. You can go to the Jansky Very Large Array in New Mexico, an interferometer that has large baseline and allows you to pinpoint it as long as you're patient. So fall 2015 with 10 hours on the VLA, nothing. Spring 2016, 40 hours on the VLA, nothing. And they were probably getting sick of us asking for time, but luckily fall 2016, in the first few hours of a test observation, boom, 10 events. And here's one of them, this paper by Shami Chatterjee et al. That we published in Nature. You can see these were the Arecibo error regions beforehand, and this is the burster in the VLA data. And so this is, and it was really unambiguous. You could see the frequency sweep there and the event. It's very, very clear. And so nine bursts in fall of 2016. The localization is now good to 1/10 of an arc second. And in fact, we went on to work with the European VLBI network and VLBA and localize even better, but I don't have time to talk about that. There's a persistent radio source at the location. I say I'm running out of time, and an optical counterpart 25th magnitude. It's a dwarf galaxy, so it's at redshift 0.2, indeed a gigaparsec. Very well localized, and a dwarf galaxy, we were shocked. Why a dwarf galaxy? Like the mysteries abound with these events. So where do we stand with FRBs? There's at least one FRB that repeats, and it's at a cosmological distance, FRB 121102. But the open questions are, is this representative? What is the bursting source? We don't know. What is the persistent radio source that's there that I glossed over really fast? And what are these related to? In the last minute, 30 seconds, I'm going to tell you about a new experiment that I'm hoping will help solve some of the FRB problems, called the CHIME telescope that we're building in Penticton, British Columbia in Canada at the Dominion Radio Astrophysical Observatory. This is CHIME. It's a new style radio telescope. Well, not really new. There's other cylinders been built before. These are 4 cylinders that are 20 meters by 100 meters, so it's 80 meters by 100 meters of collecting area. In Canadian units, that's the area of 6 hockey rinks. Along the axis of each cylinder, there are 256 dual polarization feeds that are sensitive to the 400 to 800 megahertz bandwidth range. So there's a total of 1,024 antennas that are the signals from which are being put into a massive correlator. The native data rate of CHIME is about 10 terabits per second, which is, I don't know, something like comparable to the phone network around the world. So it's a very large correlator that is going to be housed in these, you can't quite tell, these are large shipping containers here that have been fitted to be like Faraday cages, massive GPU cluster and FPGA clusters. What's really important here is that the field of view, thanks to the style here, these cylinders are oriented northwest, north-south, you get about a few degrees directly overhead. So there's no moving parts here, no moving parts. It's a transit telescope. You see a few degrees east-west overhead, and the Earth rotates through it. But the beauty is that you get something like 120 degrees north-south of field of view. And funded by the Canada Foundation for Innovation. Very, very quickly, if you just put one antenna on one cylinder, your field of view looks like that. That's sort of the primary beam. You could think of it as that. If you then populate one cylinder with many little antennas, then you do FFTs along the north-south direction, and you can break that field of view up into many little beams. And then if you populate everything, you get 4 east-west and 256 north-south beams. So CHIME's roughly 220 square degree field of view, whopping massive square field of view, wide bandwidth, large collecting area, mean it can detect something like a few FRBs per day once we get this operating. And I should just tell you, as some of you probably know, this telescope was designed for totally different reasons to study dark energy, measuring baryon acoustic oscillations. But you can see, it just turns out it's a wonderful FRB machine. So we're really looking forward to that turning on. The conclusions, FRBs are here to stay. Their origin remains unknown. Perhaps they all repeat, we don't really know. The first localization is accomplished and the cosmological distance is confirmed. And finally, CHIME will be a great FRB machine. And I thank my students at McGill, students and postdocs at McGill, the CHIME team, funding agencies, and I will leave you with a drone flyby of the CHIME. Thank you very much.
All right. We have time for a couple of questions.
Hi, so what's the radio distance resolution you can determine for the repeated FRB? Like you say, it's like you can determine it to 900 gigaparsec, but what's the resolution for the distance?
Well, the redshift is really well known for that galaxy. So it was like, I think the redshift is measured to a part in 10 to the 4 or something like that. So I'm not sure exactly what distance resolution that implies, but it's very well, similar, part in 10 to the. It's very well determined for that one event, for that one source. I think.
Thanks.
A question up here.
What multi-wavelength observations could maybe help to pin down the origin?
Right. So I don't see where that question's coming from, but multi-wavelength observations, yeah. So we would love to be able to look for optical counterparts. That's a possibility. There are currently attempts to do that. The problem is that radio waves are dispersed. So you have to work in the past, meaning that if the optical and radio were simultaneous, we're only detecting the FRB after the event because of the dispersion delay. So you have to be observing the same field at the same time, and that's a challenge. In X-rays, there have been attempts. The paper by Schultz et al. Is now out. Chandra observations simultaneous with a radio burst, and no X-rays were seen. I think there's attempts to look for gamma rays from them, but I'm not sure of the status of that.
All right. One more quick question.
At what point do you think CHIME or HIRAX, once they reach full operational capabilities or even beyond, could actually do this sort of location of FRBs and galaxies with just one event?
Yeah, so for CHIME and HIRAX, the angular resolution on the sky, even with the huge processing and everything, is still only arc-minute scale. But on the other hand, if we had like outriggers, And we could do detect with effectively VLBI techniques the event in real time, then we could localize it in real time also. And so that, I know HIRAX is thinking of doing that. We are thinking of doing that. In fact, there's some effort to get that going. It's actually Wei Li Pen who's really working hard at that with the Algonquin radio telescope. It's a large radio telescope in Algonquin Park that he's sort of gotten going again. And so the idea is to try and correlate CHIME with ARO. That we haven't actually accomplished that yet, but that's the hope.
All right. Let's thank Victoria again.